probably by next Thursday. I will send you an email, so that will give you a week. And I'll also post the solutions for this so that you'll be looking at them for that. Okay. But I will confirm the Thursday. It won't be on Tuesday, so do show up for the class on Tuesday. Okay, so that's, and then as I said, it's going to be basically up until the end of Bayes networks inference, not the learning part. So the part that we've been doing in the last 2 classes is not included. Okay. Any questions before I get started? Okay. So we were looking at last class. Mostly we spent time going slowly through the ML-based learning, basically maximum likelihood based learning of the parameters for Bayes networks. Okay, and then started talking about how to go beyond that to talk about topology. Okay, so that's where we're going to start again today. As a sort of a quick review, this is basically these are the steps involved in trying to learn parameters by maximum likelihood. Okay, and we did these steps for the examples. The 2 examples we looked at. One is the single node example, the other is the multi-node example. Okay, so in essence, the first thing you need to do is you need to be able to write down an expression for the likelihood of the data as a function of the parameters. Okay, so for example, you did that here. This is the likelihood of the data as the function of parameters. Right? Next you do, then you take basically a log of it. Okay, so in doing this, essentially you take into account the fact that all the data are independent and identically distributed, and so you essentially can multiply, given the data, given the hypothesis, the data are independent of each other. So you can multiply the likelihoods to compute the combined likelihood. Okay, and then you take a log, and then you're trying to maximize this expression, the likelihood expression. So you take the log and you maximize that normally. That's what you're supposed to. That's what you try to do. And then so to do the maximization, of course, that's just normal, continuous function optimization. Okay, because in most cases, what you have is this function. This is a function in terms of the parameters, and so really it's a continuous function because the parameters they are probability parameters, so they can take values between 0 and 1. Okay, so you are talking about optimizing a continuous function, and the theory for optimizing a continuous function is you look for where the gradient becomes 0. Okay, and then in the simple scenarios, just looking for where the gradient becomes 0, so you compute the gradient and equate to 0. So the gradient for a single variable is just a normal differential. For a multivariable function, it would be a set of partial derivatives. You set all of them equal to 0, and then you get a bunch of equations. Okay, if those can be solved analytically, you are in good luck. If not, then you essentially are trying to find the roots of that equation. And trying to find the roots of the equation, you can use Newton-Raphson Method, for example. Okay, if for the cases that we looked at, which is basically normal Bayes networks with discrete conditional probability tables, then essentially the partial derivatives will all, when you equate them to zeros, they will all become uncoupled equations. Okay, in particular, people talk about what's called parameter entanglement. Okay, so a set of equations, these are a set of equations in terms of the parameters. And here the equations, the parameters are unentangled, right? Because this equation is only about theta. This is only about theta 1. This is only about theta 2. Normally, if you have simultaneous equations, that's not going to happen, right? Simultaneous equations would have things, like this will have both theta 1 and theta 2, and so on. But this is the easiest case of simultaneous equations. What basically you found is for Bayes networks with discrete probabilities, with basically CPTs, the parameters become unentangled. And so it's very easy to find, you can compute each of them separately. Okay? And then you're finding the parameter values such that the derivatives are equal to 0, and then that's your maximum for the likelihood, and then that's the parameters you set. Okay. As I said here earlier as well as today, there are two ways in which this step can become complex. One is the individual partial derivatives lead to nonlinear functions. They don't have to be linear. So in this particular case, it turned out that these equations are all linear equations. Okay, they could have been nonlinear equations. And nonlinear equations, finding roots of that is harder. I mean, you just about know how to find roots for quadratic equations from probably grade school and high school. But higher order ones, you need to use numerical techniques. Okay? So basically, individual partial derivatives can become nonlinear functions, and so when you set them equal to 0, then you're solving nonlinear equations. The second is that the individual partial derivatives might involve more than one parameter, in which case they truly become simultaneous nonlinear equations. Okay? And this is the general thing that can happen when you're learning, probabilistic models. But for Bayes networks with CPTs, it won't happen. That's why you are happy. Okay? And if in fact the general thing does happen, as I mentioned towards the end of last class, then you essentially have a set of nonlinear equations and you're trying to find the zeros for it. Okay? If I give you a nonlinear equation in a single variable and you're trying to find the zero for it, that is the place where it cuts the x-axis, right? You can use Newton-Raphson method. Okay? And all that says is you start with any random point. So basically, guess a solution. Guess a solution to be the zero. And most likely you won't be correct unless you are like the luckiest person on earth. When you put that value into the equation, it becomes equal to 0. For the expression, it will become equal to 0. Most likely, that won't be the case. Then you need to improve your guess. Okay? This is sort of local search. In combinatorial search that we talked about, when was the last, did we talk about any local search at all? Hill climbing. Which algorithm did we talk about for hill climbing?
Lowest K.
What?
Gradient descent.
Now, gradient descent is what you're doing here. We did not do gradient descent in combinatorial search. We did hill climbing in the case of SAT problems. Okay? We used the number of, you start with a complete assignment and see if it already satisfies all the clauses. If so, you're done. If not, you're going to make a local move by flipping one of the variables. The question is which variable to flip. Okay? And you would pick that variable to flip, which basically increases the number of clauses satisfied. So the gradient that you're following there is the number of clauses that get satisfied. Okay, so that was the local search that we used in the SAT problems. In some sense, interestingly, we pretty much did only systematic search for the most of the time we talked about search. That means you consider all branches until exhaustion, until you find a solution. Right? A-star search is like that. So is depth first search, and although it sometimes gets into loops and so on. And certainly breadth first search is like that. Okay? And so in fact, the only exception that we saw was this local search. One algorithm we saw for local search, which was this min conflicts. There are actually lots of other local search algorithms too for combinatorial search. Now, think of trying to do systematic search for a problem like this. You can't do it. For a continuous function optimization, there is no such thing as systematic search because you can't branch on all possible values x can take. There are infinite possible values. Okay? In continuous function optimization, pretty much the only theory that is out there is local search. And the basic local search that you do here is you are essentially following the gradient, which is defined as the derivative, which is defined as a partial, the partial in terms of the derivatives and partial derivatives. Okay, so that's sort of the interesting connection. So we talked about two kinds of searches. One is what is called combinatorial search. The search that we talked about in the beginning of this semester is combinatorial search. There are only so many different states that are possible, discrete set of states. There can be infinite number of states, but there are discrete set of states. Here, there are infinite number of points, and they're dense. So you can't actually even branch. So pretty much the only thing you do in continuous function optimization is local search. Okay? I mean, you knew this, but I'm just trying to force you to put those two parts together. We are always extremely good at keeping this part here, and going through life so that they don't mix. By mixing is when you realize the patterns. Okay? Okay, so in this case, you could have used the Newton-Raphson method, which essentially says if you start from here and it's already not 0, then you need to kind of, this is not the correct value, so you need to go towards this. You can see here what is the right value. But the question is, how do I get here? One idea is start from here and subtract f of x by f dash of x. And that will essentially get you somewhere here. Basically, this is the slope of f dash, slope of this function at this. Right? That's what a derivative does. Okay, so anyway, you can compute that next value and then next value. And Newton-Raphson has a very nice way to converge too, because as you come closer to 0, essentially it makes smaller steps. Because closer to 0, f of x will be close to 0. You see what I'm saying? Okay. Now, of course, you're going to use the same Newton-Raphson for the derivative. So you will start, f double dash. So instead of f of x by f dash of x, you do f dash of x by f double dash of x. That's what gets done in more intensive, more complex cases of learning probabilistic models. Thankfully, we don't have to care about it for this class. Okay. Now, the other thing that I mentioned is that till now what we have looked at is situations where the topology is completely given and the data is completely known. And if you are looking at Bayes networks, then your life is very simple. You essentially just count. Okay? Now, if the topology is not given, so for example, consider an example like this. Okay? You are used to different models, like for example, Russell model. Not Russell model, the Pearl model, where I told you a story about Pearl and his house and earthquakes, etc., etc. And you had a sense of if there is a network, what should its topology look like? Okay, but generally, you could have a situation where all you have is data and no information whatsoever about what the causality is in that domain. Okay, and so you are trying to figure out both the topology and the parameters in general. Okay, so an example that I'm using, because I'm going to use this for other parts of today's class too, is this silly example called Russell's restaurant waiting habits. Russell wrote the textbook, so he made up this example about himself. Okay, so he essentially is basically he self-observed himself, or like somebody who is trailing him, stalking him while he goes to various restaurants, observed him as to whether or not he waits for a table at a restaurant. Okay, the idea is in this case, so there are a bunch of attributes about the restaurant situation that seem to matter. Okay, so for example, is there an alternative to that restaurant? Okay, and is there a bar at the restaurant? Is it a Friday? Are there anybody in the restaurant? Is it a very costly restaurant? Is it raining outside? And what's the type of cuisine? And how long am I supposed to wait? He somehow realized that these things seem to matter. Okay? And so for each example restaurant scenario that he has gone through in his life, he wrote down the full example. Okay? So this example X1, there is an alternative, there is no bar, it's not a Friday, and I don't remember what HQN is. And then there are some patrons in the restaurant, okay? And then their price is very high. The restaurant is a pretty costly restaurant. It's not raining outside. He does have a reservation, and it's a French cuisine, and he only has to wait for up to 10 minutes. And then on that particular case, he actually decided to wait. Okay? And then there is some other case like here, where there is no alternative. Okay? And then there is a bar, and it's a Friday, and the restaurant is full. It's a cheap place to eat. It's raining outside. He does not have reservations. It's a burger joint, and he has to wait for more than an hour, and he decided not to wait. Okay? So I give you a bunch of examples like this. And if you are Russell, then like the most important problem for you is to predict later on, given a new restaurant scenario, will I be waiting or not waiting? Okay? So this is actually just like data. So in some sense, in the burglary, earthquake, alarm, John calls, Mary calls, it didn't look like any one of these variables are any more important than any other variable. Okay? But I can always say somehow that my most important question is, will Mary ever call me? Then all I really care about is under what conditions does Mary call me? Okay? And so will Mary call me if the alarm goes off? Will Mary call me if John calls me? Will Mary call me if there is an earthquake, and so on? So my entire world now revolves around Mary calling me. And so I'm just going to classify every new situation as yes, Mary will call me, no, Mary won't call me. Do you see what I'm saying? And the same thing here. So you can either say all of these are equal sized and equally important attributes, or you can say there is a specific attribute that you are particularly interested in predicting. Until now we generally said we just want to predict the data completely. Right? I've seen some data and I want to predict new data. So in fact, one of the interesting things about learning Bayes networks is, suppose there is a Bayes network for this. Then you can the Bayes network will generate entire sets of examples like this, which are indistinguishable from the real examples. Okay? And those are called essentially generative models because they generate the entire data. If you generate the entire data, you also happen to generate the one particular attribute that you are most interested in. Okay? In many cases, you happen to be particularly interested in one variable, and so you can still predict it using this approach. But as you might be thinking as I'm doing this, isn't it like too complicated a thing to do? If all you care about is this variable, must I model the entire data? Must I have a Bayes network that models the entire data? Okay, which is an interesting question, and we'll get to that soon. Okay, but for now, let's assume that I have a way of learning Bayes networks, and I want to learn a Bayes network for this. And if I did learn the Bayes network for this, then if you gave me the values for the x20, you gave me the values of all these other variables, I can predict whether or not, what's the posterior probability that Russell will wait or not wait. And if the posterior probability of waiting is higher than not waiting, then you will say yes, he will wait. If it's lower, you'll say no, he won't wait. And you can also talk about your confidence in your prediction. If your prediction on the posterior probability that he will wait is 0.500001 and 0.499999, that means you're not particularly sure of your prediction. Okay, you can even actually talk about the confidence in your prediction. Okay, you understand this, right? Now, this kind of problems we'll see in a minute. They are also called classification problems because essentially I'm trying to classify this entire data in terms of will the variable here be yes or no. Okay, a classification problem is typically a special case of data prediction problem. As I said, in this case, you could be interested in predicting the entire data, or I could say all I care about is whether Mary will call or not, in which case all I care about is predicting Mary calling. The rest I don't care. Okay, now having come to this example, my question is, suppose if I'm trying to learn the Bayes network for this, what topology am I supposed to use? Clearly, I don't know. I don't even have a reasonable idea. You see what I'm saying? Okay. So you really have to try various types of topologies and see which one will basically have the most which one, when given the right parameters, will give the most likelihood to the data. Okay. And that's what we were saying with respect to this slide last class. Okay. When you have multiple topologies, when you don't know the topology, and so there's nobody to give you the topology, then you essentially have to consider learning over all possible topologies. So as I was mentioning last time, if I think there are only two topologies possible, this is one, this is the other, then I will find the best fit parameters for this topology, and then with respect to that, what is the maximum likelihood what's the likelihood for the data? Best fit parameters for this topology, with respect to that, what is the likelihood for the data? And the likelihood is the score, really. So now you put two tournaments. This is one league, this is another league. In this league, the ML parameters will be the winner. And that winner score is the likelihood that particular network with those parameters will give to the data. And for this, the same. And now you can compare these two likelihoods, and whichever gives the higher likelihood to the observed data is the winner. Okay? This is basically the idea, and as I mentioned last time, the complication, of course, is that in general, if you compare this to this, you'll always see this will win. Because this has more links than this. And it can be shown that when you add more links in a Bayes network, then you cannot reduce the likelihood of the data by adding links. You can only increase. Which essentially means that as you are trying to compare, if you do it this way, when you are comparing the topologies, the one with the more links will always win. Which also means that in most cases, you will wind up picking networks that are fully connected. And that can't be right. Why should it be the case that in the world everything affects everything all the time? I know that's a conservative thing to do. Assuming that everything affects everything is a conservative thing to do. If you're paranoid, hopefully you can never be caught in a surprise because somebody did bad things to you, because you're already paranoid. Okay, you're thinking everybody is going to do bad things to you. Okay, so you'll never be caught in a surprise. But of course, paranoids have a very slow lifestyle because they cannot go anywhere, because anything they do, they're expecting that bad things will happen to them. Okay, so similarly, if you have a network that's fully connected, essentially it's a very inefficient network. If in fact the world does not require those many dependencies. Okay, so your learning algorithm should be able to differentiate. And this is where I mentioned last class that to distinguish between this topology and this topology, you need to realize essentially that all topologies are not created equal. Which is what you said when you went from Bayesian learning to map to ML. And you get to ML from map by saying all topologies are created equal. So basically I have a uniform prior. And so obviously you didn't mean that. So the right way of doing topology learning essentially involves providing again a prior term that depends on the topology. Okay? And that is basically, you can think of that as a penalty for the network structure. Okay? And the more densely connected the network, the higher the penalty would be. And the assumption is you can always fit the data by putting more and more links, but you should know when to stop. Okay? And that's basically the kind of search that happens when you're searching for the best topology. Okay, so you need to have like a penalty metric, and then you do local search in the space of topologies. Typically, people do local search in the space of topologies. Pick a topology, find the maximum likelihood parameterization for the topology, and if they say, give me a network right now, you stop thinking, just give that. If they give you more time, then you essentially consider making changes to this network topology by either adding or removing networks, adding or removing links, and you have now a new candidate. And the new candidate has a different penalty from the previous one. If it has more links, it has higher penalty. If it has fewer links, it has lower penalty. Okay? And then find the maximum likelihood parameterization for that. And then see what it says with respect to the data. And if the new candidate's likelihood given to the data is worse than what you are giving, then you stick here, you don't go there. That's hill climbing. So hill climbing, not in the space of altitude, but in the space of likelihood given to the data. Okay? Okay, so that's how topology learning works. Basically I'm just trying to get you to understand that I'm not giving you an actual algorithm. Okay? Another way of dealing with this is what I want to talk about right now, which is this is the right way to do it, which is actually learn the topology. The other way to do it is what I call the Jean Harlow model. Does anybody know Jean Harlow here? Jean Harlow is this Hollywood actress who's, as far as we are concerned, her claim to fame for today's class is that she is reputed to have said once to her boyfriend that whatever you get me for Christmas, don't get me a book. I already have a book. Okay? And basically, what you can do is don't give me a topology. I already have a topology in mind. Okay? And so, irrespective of the data, I'll always use that topology. Okay? That's what naive Bayes classifier does. What naive Bayes classifier does essentially is, if in this particular case, notice that this is a kind of a classification task. So whether, it just assumes that one variable sits in the top, every other variable is in the next level, and this one variable causes every other variable. That's it. That's the model it assumes. In a classification task, the variable to put at the top is obvious. The most important variable is the one that's put in the top. Okay, so here is the will weight variable, and then every other variable, the alternative bar, Friday, blah, 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 everything just comes underneath. And then, will weight is connected to every one of them. That's your Bayes network. That's it. Okay, now how many parameters, and since you came here having learned, most people learn about naive Bayes classifiers just from scratch, like from, here is an example, here's what we'll learn. But we are coming to it in a much more, more intense, kind of more with deeper understanding of learning Bayes networks. Okay? You're coming to it, and you see this as a kind of a network, where you essentially said, don't give me a topology, because I already have one. And that's all I will fit you. Irrespective of what your real topology is, this is a topology I'm going to fit you. And I'll always be able to find the best parameterization for that topology. And in this case, how hard is this going to be? This is a complete topology. I give you a topology, and this is complete data. All data is known. So I can compute the parameters, for this, for example, will weight needs a probability will weight is true, and probability will weight is false. And that, how do I compute that? Count the number of examples in which will weight is true, divided by the total number of examples that are present. That will give me the prior probability of will weight. That's it. Is that the right thing to do? Yes, because we went through this whole motions of doing maximum likelihood based parameter computation for Bayes networks. And this is a Bayes network. Okay? Right? And then similarly, if I need to compute, so here is my, here's my Russell example. Here is my naive Bayes classifier. This is what naive Bayes classifier will do, a naive Bayes model will do. Naive Bayes model will put the class, if it's a classification task, the only difference between classification and general learning is in the classification you assume a particular variable is important. You want to actually predict that. In general learning, every variable is just equally important. And all that matters from a naive model point of view is you have a model like this. One variable at the top, everything else in the bottom, and then there are links from, and then this parent variable causes everybody else. If in fact it's a classification scenario, you basically put the class variable here and the attributes here. And so you're acting as if all the attribute values are caused by the class variable. That's all you're assuming, acting, okay? So now, as I said, given this, to actually compute the parameters for this network, I need to provide the CPTs at each of these points as well as here. And the CPT for here is P will weight equal to yes, that's 6 by 12, because there are 6 examples in the data where you are actually weighting, and there are total number of 12 examples. So 6 by 12 is the probability that you'll weight. That's the probability I'm going to put in this model. I could have put any other number, but none of them would maximize the likelihood of the data. Okay? And then how about this P, the probability that pattern is equal to full given will weight equal to yes? Because one of these will be patterns, right? And then there's a will weight connected to patterns, and then at that node I need this probability. P pattern is equal to full given will weight equal to yes. How do I compute that? I essentially look at the patterns column, okay, and consider all the rows where patterns equal to full and will weight. So here, so patterns equal to full and will weight equal to yes. The rows in which both patterns equal to full and will weight equal to yes are 2 of them. Divided by the total number of rows where will weight equal to yes, which is 6, 2 by 6, 0.333. That's it. Okay, so in some sense, in any other classes where some of you, if you take data mining classes, etc., you will have a separate way to learn naive Bayes classifiers. Here it just comes out as a cheap corollary of the much more complex thing we learned, which is learning any kind of Bayes network. And if you do this, naive Bayes classifier is just, don't tell me the topology, I'll just compute, assume this one topology and I'll compute the parameters for it. That's the point, yes.
But this model is like counterintuitive, right? This cannot be a causative model, right? How can will weight?
No, what's more interesting is you have no clue what. First of all, here's a very important point to understand, that although I said that in real world domains, if you happen to know the direction of causality, putting the variable, the arrows in the direction of causality is the useful thing to do. You also know that the direction has nothing really to do with causality, right? Because after all, both this and this are Bayes networks. You see what I'm saying? You would like to act as if Bayes network, the directionality of the arrow is causality, but that's not required. All I said was, if you happen to know the causal direction, pick the Bayes network configuration which follows the causal direction. Because why?
Reduces
Probabilities are more robust.
Exactly. That's the reason. Remember that. Causal probabilities are more robust. So if you assess them, they're not likely to change from tempi to, so if in fact runny nose is caused by flu, then the probability with which runny nose is caused by flu will remain the same whether you are in Tempe or in Durban or in Delhi. That's the reason you go with probabilities, with the causal direction. But if you don't know what causes what, then these both are Bayes networks. And in most interesting, the interesting part is that Bayes network learning is used sometimes to learn the causality in the domain. But that's blind leading blind. Right? In fact, there's a whole entire areas like bioinformatics, etc., where people have tons and tons of data. And they don't quite know what causes what. And so they ask you guys who have completed AI or machine learning and say, why don't you find me a good Bayes network model? And so you will use topology learning and figure out that this model seems to work better than this model, and you give it to your colleague. Now then the colleague basically thinks, okay, maybe this is the causality direction. The good thing, of course, then is if I give you a possible model as a causal model, I can check whether that is a causal model or not. So in the case of bioinformatics, then in biology, then your biology colleague will do the wet lab experiment to see whether or not this causal direction actually holds. And the interesting point about causation, of course, is there is this notion that if you stop the cause, then the symptom would stop. So the notion of intervention holds. Can you intervene so that the symptom won't work? And when you can do that, then there is more, there's reason to believe that that's a causal direction. But all I'm saying now, this is a long-winded way of saying you will never really know, what is the, the direction is not supposed to be. I mean, just because the Bayes network has an arrow doesn't mean that's a causal direction. I'm just saying if you happen to know the causal direction, put the arrow in that way. But you could put the arrows in other ways too and still get Bayes networks. Okay? And in the case of my Bayes classifier, it's not only that. In fact, the right model for this domain may be any arbitrary network over what? How many variables? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So any directed graph on 11 variables may well wind up being the optimal Bayes network for this. And since that's too hard to deal with, we'll just assume this is going to be the model and we'll find the best parameterization for this. Okay, this is almost like saying, again, they say that for a guy with a hammer in the hand, everything looks like a nail, right? They say nail or not, I have a hammer, it looks quite like a nail. Huh? And the same thing here, so if you have naive Bayes classifier as your model, naive Bayes model as your model, you will find the best fit parameters for it. Okay. Now the reason I actually wound up saying it this long is, even though this is an obviously patently silly idea to assume that the world that you don't know follows actually a naive Bayes model. The reason I said this is because presumably it actually works in practice. And true, it does work in practice. In fact, naive Bayes classifier is one of the cheapest ideas that's just darned effective many, many times. And there are papers written trying to understand why does an idea that's not supposed to work. And part of the reason it turns out is if you got the wrong Bayes network model, actually it's a naive Bayes classifier. Naive Bayes models are good for classification. They're not good for entire data prediction, but they're good for classification. And for something to be good for classification, all they need to do is that the posterior probability for will weight should be such that the correct value for will weight is slightly more higher probability than the wrong value of will weight. Do you understand what I'm saying? Suppose the true, given some actual evidence on these attributes, the true posterior probability for will weight is 0.9 and 0.1. That means 0.9 is will weight, 0.1 is not weight. And your algorithm, the naive Bayes classifier, came up with a posterior distribution which said 0.50001, 0.49999. In terms of how bad its inference, how bad its guess is with respect to the posterior, it's pretty darn bad. In terms of how bad its guess is in terms of prediction, it has no error. It picked the right answer. This is why you guys want multiple choice questions. Right? Right? This is because if you have multiple choice questions, in fact, when I ask true and false, when I ask true and false questions, I write always on top that you won't get any points unless you justify. And if you give the right justification and put the wrong answer, you'll get full points. If you put the right answer and put the wrong justification, you get 0 points. That's why nobody takes my class. But the point is, people love true false because you may not quite know the real reason, but you think, maybe it's true. Or maybe it's false. Maybe there are so many truths up until now, it must be false by now. Right. And it seems to work. You see what I'm saying? Okay, so these are good questions as to why do these kinds of crazy assumptions work in practice? And there is actually a great paper on phenomenal success of naive Bayes classifiers in practice. Okay, but I mean, many good ideas are like this. We tend to think in terms of linear constraints. Is world made up of linear things? No, it's mostly made up of nonlinear things. We do linear because we know how to solve them. That's basically like the drunk searching for his lost keys under a lamppost because that's where the light is, not where he lost them. I lost them somewhere there, but that's too dark and I can get mugged. So let me check under this, under this light. And we are doing this, and it has no reason for the world to behave in such a way that our assumptions about it work out. But it seems to. That's the interesting part. If not, we won't be here having this class, right? Because we have very small brains. Despite what we think we have very small brains, and we had to make all sorts of assumptions to get by. Okay. Anyway, so that's the story of naive Bayes classifier. And of course, this part is not even needed for you guys, because if I give you the parameters of naive Bayes network, you know how to do inference, right? And it's just obvious. It's like reduced to something else you know already. Okay? So that's the richer way of understanding naive Bayes classifiers. Any questions? Any further questions? Okay, now with respect to that, the smoothing in naive Bayes classifier, I mentioned this also a little bit in the last class, and I'm saying it again now. Basically, instead of having a prior, you sort of assume there is an extra number of virtual samples. So when you're doing, for example, for naive Bayes, especially classifier, you're trying to find what is the probability that a particular ith variable will have jth value given the class variable is ci. Okay, the class variable has ith value. Okay, and to do that, the denominator would count the number of examples where the class variable has that value. The numerator will count the number of examples where the class variable has that value and the attribute variable has that value. You normally would do just ret divided by ret. To smooth, you add an m here. You act as if there are m more virtual examples than the ones you have seen. And then you have to make an assumption as to how many of these m examples are likely to have ai equal to bi. If you happen to know that certain values for an attribute are more likely than other values, you can just set that variable, that probability. So basically what I need is the probability P that AI will have the value BI. Okay, if I don't have any better idea, I can assume that P equal to 1 over the number of values that attribute can take. That means all values of the attributes are equally likely. If the attribute is Boolean, P would be 0.5. If the attribute is ternary, P would be 1/3, and so on. If you know better, you can use those probabilities too. Okay, but so this will give you a way of smoothing. Okay, and if the number of examples you have seen is much larger than m, eventually the effect of m and mp will just wear out. But for the small data case, it will ensure that you won't put zeros when there shouldn't be any zeros. Okay, and in the case of actually naive Bayes classifier in particular, even a single zero is bad news, because in essence what happens in the naive Bayes classifier is you're essentially going to multiply the conditional probabilities. That's what you would do if you just do normal inference. And if you have 1 0 in a product, everything becomes 0. Okay, so even from a technical point of view, it's very important that you don't get zeros for naive Bayes class, and this is the way you stop the zeros from coming. But a more deeper reason really is, you know that the number of examples you have seen may be too few, and so jumping to conclusions just based on those could get you the wrong parameters. Again, it too is due to the same original sin, where we essentially said the prior doesn't matter. Okay? This part basically is just a particular learning algorithm called naive Bayes classification. It just fell through for us, it fell out as like a corollary of something that we already have known. Okay? Now, the next thing I wanted to do, actually if I take probably the rest of the class, is again a very interesting idea, is what happens if you don't have complete data. So remember that the case for Bayes networks is very easy if you know the topology and you have complete data. Complete data means every attribute's value is known in the training sample. That means in the case of burglary, earthquake, alarm, John calling, Mary calling, I know what is burglary. Each example will tell me burglary's value, earthquake's value, alarm's value, John calls value, Mary calls value. And in the case of Russell example, every example has values in every column. So if you think of this as a table, there are no null values. You can't say, oh, on that particular day, I didn't quite know whether it was raining outside or not. You can't say that, because that way it will become incomplete data. We sort of assume that the data was complete. That's what data being complete means. Okay, so the question is, assume that, so there are two different difficulties. One is regarding topology, one is regarding complete data. We looked at the topology part. We looked at how to do it right. We looked at how to do it wrong, which is just say, I have a topology, that's what I'm going to fit. But that's also a pretty reasonable way to go about it, because naive Bayes classification actually works quite well. Now, when I'm doing incomplete data, that means data is not complete. For now, at least, I assume topology is given. So let's assume topology is known, but the data is not complete, and understand why it becomes a hard problem. Okay. Now, so here is a network. Is this a Bayes network? It is a Bayes network. This is actually a Markov chain in this case. Okay. So A to B to C. Even I think of, anytime I see an arrow, I assume A causes B causes C, knowing fully well that is gobbledygook. Okay. Unless I know about the world where I'm living in, I can't be sure that the direction of the arrow actually agreed with the causality direction. Okay. So here are my examples. Training examples. In one example, A is 0, B is 1, C is 1. Another example, 1, 0, 0, 1, 1, 1, 1, I don't know, 0. So this is the training data I gave you. What would you do? Would you just give up, saying my assumptions didn't hold, I'll just forget doing anything? The most obvious thing you could do is to say, I'll close my eyes as far as this flow is concerned. I'll assume as if this flow didn't exist. It's training data, for crying out loud. Do you see what I'm saying? I gave you 16 worked out problems, and the 16th one step was missing. You could say, Rao gave me a homework problem for which a step is missing, I don't need to prepare for the exam. Right? Because completely, I'm only supposed to know if all the examples are worked out and I can learn. And one example, some steps are missing, I don't need to prepare at all. Doesn't work very well. Right? What do? I'll say, to heck with this, I'll not look at the 16th one. I'll look at first 15, so that hopefully I'll learn something, and then at least I can do the exam. So I have act as if, even though Rao acted as if he gave me 16 examples, he really only gave me 15. One is missing. One is incomplete. That's a reasonable thing to do, right? Now, obviously, you would have been happier in a world where Rao gave you 15 completely worked out examples. Actually, I think you would be unhappier, but you guys don't like examples. But if you really want to go through the worked out examples, then probably you would have been happier in a world where all 16 examples are completely worked out than in a world where only 15 are completely worked out. But a world where 15 are completely worked out beats the heck out of a world where no examples are available. Okay? So the simplest idea would be ignore this, use the rest to learn the model. Right? Okay? I can do that. So just consider the complete data as the training data. So you have a little less training data now. With respect to that, I have basically the simple case of known topology complete data. I compute the parameterization for ABC. I have a new Bayes network now. Now what happens? It can be done right now. Or you can be one of these eager students and say, hey, now I have figured out how 15 examples have actually been worked out. I can figure out what is the missing step in the 16th example. I'm not as dumb as I was before I started looking at these examples. Now I know how these examples are supposed to be worked out. Using my learning, I can now complete the 16th example. Right? So first idea would be to just take the complete data and then go ahead and learn the parameters with respect to the complete data. That's like you training yourself on only the 15 problems. And then second idea is, but now we have the parameters for the network, I can infer the missing value for this guy. Right? I mean, imagine there are like a million training examples, one is incomplete. You should have been able to get a pretty darn good Bayes network with million minus one complete training examples. Using that, you should be able to complete this data with very good accuracy, if learning has any hope at all. The same thing, if you understood 15 examples, you should be able to complete the 16th example's missing step. You can't be completely sure, but you have an idea before. Okay? So I can go ahead and infer this missing value. Now comes the question. Like the non-eager students basically probably didn't even look at the examples. Some somewhat eager students looked at least the first 15 examples and figured out how they work. And slightly more over-eager students used that knowledge to figure out how the missing steps in the 16th example work. And then there are really, really eager students who then say, hey, now I kind of figured out how the 16th example's missing step works. Now that means I now have more data, so let me relearn the entire material. Right? So now, in this case, if I were to complete this, now I have more data, more training data. So I should relearn the network. Okay? So now that we have inferred the missing value, we can recompute the parameters. Are we done? No. Now we have a better network, so we recompute the missing value again. And now you have a better understanding of what this missing value is, you recompute the network again. Until 10 years after the exam is completely passed and you are now a wise man. You really learned the idea. But this makes sense in some convoluted way, right? So you're trying to use the complete data to infer the missing value, and once you infer the missing value, remember what happens when you infer the missing value. This is a probabilistic learning, right? So will you say it's 1 with probability 1 and 0 with probability 1? No. You're likely to say 1 with probability 0.7. 0 with probability 0.3. So actually this example has become two little examples. One example where it is 1.70. Another example which is 1.30. These are fractional examples. When did you see fraction examples in this class? Most recently. What? No. Basically, I'm talking about fractional examples. Okay, think of examples as samples. When did we see fractional samples? I can give you white paper as the exam, it seems to me. Likelihood weighting. Remember? Right? Rather than say the example is completely wrong because it doesn't agree with one piece of my evidence, I will essentially consider that example to be a 0.1 weight example or a 0.3 weight example. So when I said, if using the parameters that I learned for the original network, if I was able to infer that this is a 0.7 probability it is 1, 0.3 probability it is 0, then essentially these are all samples with weight 1, 1, 1. And then this gets split into two samples. One sample 1, 1, 0 with weight 0.7, another sample 1.30, I'm sorry, 1, 0, 0 with weight 0.3. So now, when you are happily counting, remember the number of examples where the attribute has this value. The number used to be a whole number before. Now it will be a fractional number. There will be a fractional denominator, a fractional numerator. But thankfully, we know floating point arithmetic. So we can still compute parameters which are, a floating point number by another floating point. This is how the parameters improve because you learned. Again, by stretching my 16 example scenario too, I would say that based on the learning you did about the 15 problems, you probably will start having a good idea as to what the missing step in 16th would be, but not deterministic idea. But then based on that, you then go back and look at some of the other examples that you already looked at to improve your understanding. Okay? So that's what I'm doing here. Okay? So, so I can basically infer this, and then I can then reweight, and then once I relearn the parameters, I can re-infer this. And when I re-infer, what happens instead of 0.7, 0.3, I might get, let's say, 0.88 and 0.12 as the distribution. And that's a better distribution. That means you know more deterministically what the missing value is than before. Right? Notice that I could have just guessed what the missing value is up front itself, really. Okay? In the following way. How often is this column 1? In the examples I've seen till now. 2/3 of the time. How often is it 0? 1/3 of the time. So I'll put 1, I can put 1, 1, 0, 2/3, 1, 0, 0, 1/3. So in some sense, I always had fractional examples. If I ignored them, I ignored them at my own peril. Same thing for rejection sampling and likelihood weighting. Likelihood weighting uses the fractional samples, so it does it does inference with much fewer examples. Whereas rejection sampling throws it out saying, oh, you're not whole number, I don't like you. Okay? So this question, of course, is I can keep doing this until this distribution becomes better and better and better. At some point of time, it doesn't change. Then you know you have reached either nirvana or a local maximum. What would you think you would have reached? You would reach local maximum. Local maximum in what plane? What space? If you said wisdom, then you are taking my philosophical examples too seriously, as against the technical parts. What matters when you say one Bayes network is better than another one? What's the coin of the realm? If I say some person is richer than some other person, do they mean they're spiritually richer? Or gravitationally richer? Or longitudinally richer? No, we have a common currency. They have a bigger bank account than this person. That's it. That's the common currency. What's the common currency for Bayes networks? If there are two Bayes networks and I say this is a better network for this data than this, which one? What is the common currency? What?
Number of probabilities?
Nah. No. We are using this. maximum the likelihood that the network gives to the data. The likelihood that network gives to the data. So as you keep doing this, what happens is the likelihood of the data keeps, so as you keep doing this, you started with some parameters, you kept changing the parameters. And what is happening is with the newer parameters, the network now will give higher likelihood to the data. And so each step will improve the likelihood until you no longer are improving likelihood between two steps. Then you say, I have reached a local maximum in the likelihood and I'll stop. Now the question, of course, is do you ever reach even a local maximum? Or would you just keep doing this infinitely? Okay? And so the question is this infinite regress or is it likely to actually terminate? Actually, it will terminate. And this idea is this beautiful idea called expectation maximization. What I just told you is expectation maximization. Okay, now the interesting question is in this case, I had this value missing. Suppose actually I had, my example was like this. 0, don't know 1. 1, don't know 0. 1, don't know 1. 1, don't know 0. The entire column is null. Is it incomplete data? Yeah, it is incomplete data. Now what that means then is this node B, it's a hidden variable. You will never be able to observe this in the training data. And the reason you have went with this is basically with that somehow you have reasons to believe that there is this hidden node B. And you just happen not to have been able to observe B. So whatever you are seeing, they are being marginalized over the possible values of B. And that's what you are observing. Now this looks like a much harder case up front, right? This looks like the entire column is missing. It's like you're delusional now. You're sort of making up variables as you go. This one looked like, well, I had a million examples of which only one example was incomplete. I could use the first million minus one to predict this. And then you would let me continue to the next step. Now I'm saying it's the same thing, even when you don't have any values. Why? Because it doesn't actually matter what you started with in the network's parameters. That's the beauty of this idea. I just happen to start with the parameters that correspond to the ML parameters for the first three examples here, right? If I have an entire column to be 0, I won't be able to do that. So what would I do then? I just randomly pick parameters prior for A and P be given A and P be given not A. I just make up some numbers. Just don't make up 7 as the number. Because if you make 7 as the number, that means you don't even know that these are Bayes networks. They should be probabilities. So they should be between 0 and 1. Any number, fine. Okay? And then you need C given B and C given not B. I'll make up some numbers for those two too. Now that I've made up that numbers, I have a theory of how the world works. So then I can fill in these missing values with respect to this bogus network. You see what I'm saying? Okay? And now I have, each one will obviously become a distribution. So if this is a true-false one, then this might become 0, 1, 1 with 0.51 probability, 0, 0, 1 with 0.49 probability. So now I have a bunch of fractional examples. Now I recompute the parameters using ML. Now I go back and infer. Now I go back and recompute. Keep doing this until my probabilities are not changing. Essentially what you really want to do is keep doing it until between two iterations, the likelihood given to the data is not changing. And you would have computed the likelihood anyway as part of computing. Once you have the parameters, you know the likelihood. Okay? The other way is none of the examples probabilities are changing. The missing value probabilities are not changing. then you say, I'm done. I have actually learned the structure of this data, even though the entire variable B is missing. Okay? To make you believe that this is actually not just made up, I'll show you this example. All I can do is beseech, request you to look at this example in the textbook. This one is again our flavor wrapper. So the scenario in this case is the only data they're able to observe for this candy is what's the flavor of the candy, what's the color of the wrapper of the candy, and whether or not the candy has a hole in the middle. But you have a reason to believe that in fact these are all being, different candies are being picked from different bags. And so bag is actually a hidden variable. There may be 2 types of bags or 5 types of bags. And different candies are being picked up from different kinds of bags. Remember, this was the original example we started with. Now, bag is not seen. I only saw the candies. So you're hypothesizing there being a bag. And learning, and so if you do believe that there's a bag, then you also assume, you also happen to know that basically that there is a bag and that the network with respect to bag is like this. Bag causes flavor, wrapper, and hole. Complete topology is known. But none of the training examples will tell you what the value for bag is. Right? So what do I do then? I will start with my training examples. And before I even start actually considering them, I will set up, I need probabilities here. I need a probability for bag being, let's say it's Boolean. So what's the probability that bag is type 1 or type 2? I need a probability for that. And similarly, I need for each of these probabilities that if bag is type 1, what's the flavor? What's the probability that the flavor is red? If bag is type 2, what's the probability that the flavor is red? And similarly for wrapper and similarly for hole. In this first step, what I did is I just went ahead and initialized the parameters. Like I said, just pick any random probability numbers. Okay? I just decided that at the 0th iteration, this particular value is 0.6. I just decided that. Okay? And all these first rows for each of them is 0.6, and the second rows for each of them is 0.4. I just decided that. By the way, just because I did 0.6, 0.4, it's not because 0.6 plus 0.4 is 1 and that's why you should do it. No, these are 2 independent parameters. In a CPT, if I give you a CPT, the numbers don't have to add up to 1.0. You understand that, right? Okay? In this case, I just happen to pick 0.6 and 0.4 because they're both less than 1. And so, right? So this now, once I did this, I have a complete network. Because I have a complete network, now I can essentially complete each of the examples to get a bunch of fractional examples. Saying, here is an example with the type 1 bag and its weight is 0.7 because the type 1 weight is 0.7 given the data, given my network. Okay? And using that, I will then do maximum likelihood estimation. And I'll get second iteration values for the parameters. Okay, now the interesting thing is, if you compute the likelihood for the data, likelihood for the 1,000 examples, okay, it increased from here to here, from minus 2044 to minus 2021. Is anybody surprised that this whole thing is negative? Why not? It's a log of a really, really small number, right? It's a log of a huge product, a product of probabilities, which is going to be really less than 1. So log of any number less than 1 is negative. So this is minus, originally it's minus 2044, it increased to minus 2021. You know what that means, by the way? These are logs, so that means orders of magnitude improvement. You improved your probability of the data got improved by about 23 orders of magnitude, just by one iteration. And you keep doing this until the log likelihood stops changing. And if you actually plot the log likelihood with respect to the iteration number, for this example, it sort of looks like this. You see what I'm saying? It very quickly went up and they sort of plateaued there. Now you might say, why didn't it become 0? Did anybody say it? Are you saying, why isn't the class ending? That's the other thing to ask. Why did it become 0? If you're such a good learner, why didn't it become 0? Right? If the data likelihood is 1.0, that's when you get complete learning. Right? And log of 1.0 would be 0. This thing is ending at minus 1980. Zero up somewhere there, beyond the 6th floor. Why didn't I get 0? What am I missing? Because there is no reason to believe that this is the correct topology. There isn't even any reason to believe this is the only missing variable. Maybe another missing variable called flying spaghetti monster stands here, who continually connects everything and changes all the values. And as I said, just because you are not paranoid doesn't mean there isn't a flying spaghetti monster, right? So that all you are able to see from this is, A, if you want to stick to this one single missing variable, this is the best you will get. This single missing variable and this topology, this is the best you will get. Because even with just this single variable, this is not the only topology. There are lots and lots of other topologies. And if you want to be paranoid, you can make up even more missing variables. In which case you can get even more topologies. And maybe one of them will actually completely agree with the data. Okay? Does it sort of make any sense? Okay? This is EM. This is probably the most subtle idea you would learn in this course. Okay? Up front, it doesn't look like at all this make any sense. This will make any sense because you're just sort of bootstrapping yourself out of nowhere. But I mean, as Martin Luther King said, it's okay to ask people to pull themselves by with their bootstraps, but it's kind of cruel to ask a guy who has no shoes to pull himself by bootstraps. And EM says, what does Martin Luther King know? He can imagine that there is a shoe and start pulling and things will start happening. Okay? Now, what's interesting really about this slide. And you need to take the follow-on course to understand why actually EM works, or spend some time understanding the mathematical basis. Okay? The guys who came up with the formal reason as to why EM works are essentially, I think, Dempster and Schaefer. Schaefer and Dempster is probably involved. And that particular paper is probably one of the most cited papers. And it was only written less than 30 years back. Right? Okay? And so you know that actually there is a reason why it works, and in fact what happens is you are trying to find local optimum in the log likelihood space. And you can do it by essentially gradient ascent. Minimum you do gradient descent, maximum you do gradient ascent. EM doesn't look like a gradient ascent because the steps that EM does are not finite, not always uniform size steps. Okay? But it is a sort of a gradient ascent, which works very well for probability distributions. And one last thing I want you to understand, and you can go off, it's just mostly a point to realize that this is the EM algorithm that we just showed. You can use the EM algorithm without understanding why it works, which you are not surprised at all, right? Because the entire industries would have gone down the drain if people had to actually understand the programs that they are writing. Right? They depend on the customers to understand why they don't work, and then tell them, right? So you can easily write EM algorithms, use EM algorithms, and you have an intuitive understanding, hopefully, right now, And then basically the E step and M step in the EM, E is the expectation step. So if you initialize the parameters, then using these parameters, you expect the missing values to be such and such. And having expected that, you can then maximize. Maximization is the likelihood maximization step to recompute the parameters, which then give you a new expectation as to what the parameters are, which then gives you a new maximization. EM actually is EM star. Do EM step any number of times. The interesting point about EM is until you reached EM, you never did inference during learning. Remember, we did inference before getting into learning. In fact, in the exam, I said you only need to know about inference. So we unentangled inference from learning. For the complete data, you don't need to do any Bayes network inference to compute the parameters. In EM, this part is actually doing the inference. Okay, so how do you figure out, if I were to tell you what is the missing value, what is the parameters for this network, now I need to figure out the posterior and back. That's your Bayes network inference problem. You need everything that you learned about inference, including the variable elimination algorithm, including the likelihood weighting algorithm, including the Markov chain Monte Carlo algorithm, any of those to do the inference. So this step requires inference, and then this step is just, the maximization step is learning. And EM makes you realize that learning and inference are not like on different ends of the, different corners of the rule. They're completely entangled. That's how your life is. Partially understand something. Using your partial understanding, you try to expect what happens in the next example, and then come back. And so you use inference and learning always together. So that's a beautiful point that EM brings up. I'll stop here. Next class, we'll essentially look at generalized learning in the sense that we'll look at the same Russell example and then try to solve it using not statistical models but other models. Okay.